I have 100 liters of nitrogen. And so in terms of Daltons, I've got 100 liters of nitrogen. How many liters of oxygen do I have? 100 liters of oxygen. Good. And so I got 100 liters of oxygen plus 100 liters of nitrogen. If I take 100 liters of oxygen and add it to 100 liters of nitrogen, how many liters of air do I have? 100. 100. And so the difference is now, if I put all those nitrogens, you know, in the same size box and eliminate the oxygens, you know, the oxygens are fewer. 80% of the molecules are nitrogen. And so I put all 80% of those nitrogen molecules in this box, and the 20% of the molecules, the oxygens, in this box. And so what's going to happen is now I don't have the collisions from the oxygen, so what's going to happen to the pressure here in this box? It's going to go down to 80% of the total, 0.8 atmospheres. And over here, what's the pressure going to drop to? 0.2 atmospheres. You know, I got a big box with 20% of the molecules, so 0.2 atmospheres. And so automatically, if I want to visualize air in terms of Daltons, this is what I visualize. You know, this mixture as. You know.
What's that word on top of the bottom first box? Next to 118.
Air. This air. All right, I can take the same mixture and try to visualize this in terms of Avogadro's. In terms of Avogadro's, what do I have? Well, how many liters of nitrogen do I have? 80? Yeah. I'm going to have 80 liters of nitrogen, that's correct. And how many liters of oxygen do I have? 20 liters. 20 liters. And so when I look at the nitrogen and oxygen, you know, I have 80 liters and same number of molecules. What's the pressure going to be? The pressure is going to be 1 atm. So squeeze down the box. And over here, the oxygen, well, 20% of the volume now. It's going to be 1 atm. So both of these are going to have the same number, or at least the same pressure. So this is going to be 1 atm. And so this is Avogadro's here. And so when somebody asks you about the volume, you know, how much oxygen do you need? Well, you have to think. You know, you have to make sure you're on the same wavelength. Otherwise, one person might be visualizing the mixture as a Dalton's, and you might be visualizing it as Avogadro's, and you aren't going to be in sync, right? But we have to get comfortable with both ways because in an experiment we're going to do in the future, we're going to first look at the mixture as a Dalton's, yeah. First look at the mixture as a Dalton's and then switch it to Avogadro's, or vice versa, I think, again. And the way we do calculations differs based on how we're looking at it, right? You know, when you put in PV equals nRT, are you putting in the Avogadro's volume, or are you putting in the Dalton's volume, right? Because if you put in the Avogadro's volume, you better put in the Avogadro's pressure. What people often do is they put in the Avogadro's volume and then the Dalton's pressure, because they don't know there's a difference, you know. You get things mixed up in calculations. And so mixtures of gases. Some equations for that. Chi is given for the symbol for the mole fraction. Chi sub A. Okay, when we collect gases over water. Let's say we're bubbling in oxygen gas in here. We collect the gas, we bubble in pure oxygen gas, it doesn't come out pure. What happens is this gas becomes saturated with water vapor. And so all of a sudden, we try to collect the pure gas, but an easy way to collect it is by an inverted bottle. This bottle used to be filled with water, and we let the gas bubble up here, push the water out. And so we trap the gas in this bottle here. But this gas used to be pure, but now when you bubble it through the water, it becomes saturated. And so we have to account for this. This is going to be a mixture of gases. And so if we want to figure out how much pure oxygen we collected, then this volume, this is going to be the volume of the mixture. And the pressure in here is going to be the pressure of the mixture, right? And so when we measure the volume and we measure the pressure, that's the volume of the mixture and the pressure of the mixture. Now, automatically, you have to think, are you going to do this as a Dalton's law problem, or are you going to do this as an Avogadro's law problem, right? And so, well, depends. It turns out that for water, when we saturate it, we're going to assume it's at 100% humidity, that gas. 100% humidity is going to have a fixed, what we call vapor pressure of water. And that is some of the water molecules evaporate, and so you got gaseous water molecules in the air, but sometimes they collide with the surface and stick. And so what we have is we have evaporation and condensation processes occurring. This is collecting gases over water, which is a classic mixture problem. And so if you go to an indoor swimming pool, like over here, it's very humid in there, right? Indoor swimming pools are extremely humid because we've reached a state of dynamic equilibrium. You know what dynamic equilibrium is? Dynamic equilibrium is when the evaporation process, evaporation leads to water molecules getting in air. And then we have the reverse process. The reverse process is called condensation, where the water molecules stick on the surface and become stuck. Well, what's going to happen is, if it's less than 100% humid, then we're going to have net evaporation. But once we hit 100% humidity, then we get enough water molecules in the air such that the rate of condensation speeds up to the point that it equals the rate of evaporation. And so we have this cycle here. It's dynamic. But what's not changing is the amount of water here. Now, the amount of water is going to be given by how big this box is. The bigger the box, the more water we have in there. But what's really dictating the condensation rate are the collisions. And the collisions can happen with the surface of the water, right? Or the collisions can happen with the inside of the room, or the walls of the container. And so what's going to happen is we're going to hit a certain pressure where the condensation rate, due to the collisions, pressures is collisions per unit area, will match. And so what happens is at 100% saturation, we get a fixed water pressure. Does that make sense? In other words, we get a fixed water vapor pressure, and we call this the vapor pressure of water. And so 15 degrees C doesn't have such a high evaporation rate, and therefore we don't need to get as many water molecules in the air in order to saturate it. And as we go to higher temperatures, the evaporation rate increases, therefore we need a higher concentration of water molecules to compensate for this. And so these are the vapor pressures of water at 100% relative humidity inside a fixed container. And so that's what we have here. We have a fixed container, and initially there's going to be net evaporation, but once the pressure builds up here, then you're going to get enough collisions to reverse that, and we get a saturated gas sample that's saturated with water vapor. All right, all we need is the temperature. And so if this vapor pressure of water is fixed, then how should we visualize this mixture? Should we use Dalton's or should we use Avogadro's to best visualize this mixture? We should use Avogadro's is tough because we don't know what the volume is. You know, the volume of water varies depending on how big the container is. So if I use a bigger container, the volume of water is going to be bigger.
You see the vapor pressure is fixed.
Yeah, the vapor pressure is fixed. So the bigger the volume, the more volume of water vapor. You know, in other words, the volume is what we call an extensive property. It's going to depend on the size of the container, whereas pressure is what we call an intensive property, because the pressure is going to be independent of the amount. If I make this box bigger, of course I'm going to have to evaporate more water to compensate, but once it hits that pressure level, then the rate of condensation equals the rate of evaporation, and we reach a state of dynamic equilibrium. And so this is regardless of how big the container is. And so what we want to do is we want to visualize these gas mixtures as Dalton's mixtures. Dalton's mixtures. Okay, so if I visualize this as a Dalton's mixture, then this is what I have. Let's say I'm collecting oxygen. If I'm collecting oxygen in here, I have a mixture of oxygen and water vapor. And so let's say this is O2 gas. This is H2O gas here. We can visualize this in both ways. We can visualize this as a Dalton's, and we can visualize this as an Avogadro's. And so let's go ahead and visualize this as a Dalton's. Okay, let's say the temperature is 25 degrees C. Then that tells me that the vapor pressure of water is 23.76 millimeters of mercury. And so the pressure of the water vapor is 23.76 millimeters of Hg. And so I got some collisions. That's not such a high pressure, right? But it's going to feel very humid inside that box. Okay, there we go. Now, this is what we're going to do. We're going to visualize this first as a Dalton's and then as a Avogadro's. So let's go with Dalton's first. Let's say, let's pick a volume. I'm going to, you know what? I'm going to pick a very easy volume, 1.0 liters. Let's say it's 1.0 liters, and I'm going to pick a very easy pressure. Let's say the pressure is 1.0 atmospheres. And so I got 1 liter, 1 atmosphere, and it's an oxygen gas sample with a. And so now let's figure out what I have here. What do I have? Okay, let's do it for Dalton's first. What do I have in terms of Dalton's? All right, in terms of Dalton's, how many liters of oxygen do I have? 1 liter of oxygen. So I got 1.0 liters of oxygen. How many liters of water vapor do I have? 1. Plus 1.0 liters of water vapor. Okay, what else do I need to know? Atmospheres. How many atmospheres of oxygen do I have? Yeah, let's figure it out. Well, actually, let's do water. Water's easy. The pressure of the water vapor in here is going to be, is it still going to be the same? Is it still going to be 23.76? We got rid of all the oxygen. So will it still be 23.76? So we can convert it to atmosphere. What is the pressure of H2O gas?
They just converted the
Yeah, we'll just leave it in millimeters. 23.76 millimeters mercury. Does everybody see that? It's the vapor pressure. If I have a 1 liter box, that 1 liter box has to increase to a pressure of 23.76 so that the condensation rate equals the evaporation rate. What's the pressure of the O2? Well, Dalton's law says the sum of the partial pressures is equal to the total pressure. And so the pressure of the O2 is equal to 760 minus 23.76 millimeters of Hg, which is equal to what?
736.24.
736.24 millimeters of Hg. And so if I want to figure out how much O2 I actually formed in this, or I actually collected, you know, this is what I figure out. The moles of O2 will equal the pressure of the O2, which is up there, right, over the volume, times the volume of O2 over RT. And so what is the pressure? The pressure is 736.24. We convert that to atmospheres. The volume is 1 liter. That's how many moles of pure O2 I formed. Okay, now let's think in terms of Avogadros. If I think in terms of Avogadros, I have some oxygen. Did I form 1 liter of oxygen? Avogadros? No. And then I have some water vapor. Did I form 1 liter of water vapor? No, not even close. And so this is it. So here's our oxygen. And we compress our oxygen here. And our water vapor here. What can I answer very quickly and easily for Avogadros? The pressure. What's the pressure of the oxygen I just collected? 1 atm. And the pressure of the water vapor? 1 atm. That's very easy. All right. Okay, but now the volume. What are the volumes I collected? We can tell. We can tell. How can we tell? We can tell easily. This is should be a simple calculation. We'll have to calculate it though. No, we don't use PV equals nRT. Well, no, not really. We don't use that either. We use a new equation that you're probably not that familiar with. VA over V total is equal to PA over P total. And so if I want the volume of component A, the volume of component A is equal to PA over P total times V total. In other words, I don't know what the percentage, what is the percentage of this? The percentage would be 2376. In other words, the percentages are all the same. And so if I got 23, let's do the fraction. 2376 over 760, right? This is for H2O gas. 2376, the pressure fraction has to equal the volume fraction. So the volume of, this is B, sorry, or we'll just say volume of H2O gas over V total, 1.0 liters. In other words, if this is 20% by pressure water vapor, then it's going to be 20% by volume. Is that? Remember, we just did this with air. With air, it was so simple. It was 0.2 atmospheres of oxygen, 0.2 liters of oxygen, right? It's the same exact thing we're doing here. You know, the percentages or the fractions have to match. And so over here, you know, this is just whatever fraction we have times the total. So it's got to be the same fraction. You know, the volume fraction is equal to the pressure fraction. And so the pressure fraction is just this, 2376 over 760 times V total, which is 1.0 liters. So this ratio, or the fraction, has to hold. And so what is the volume? Point 0.031 liters. So the volume here of the H2O gas is quite small at 0.031 liters. And that means the volume of O2 is a remainder, so it's 1 minus that. And so it should be 0.969 liters. Right? In other words, we could have done a second calculation. In other words, this. 736.24 over 760 should equal 0.969 over 1 liter, right? These two fractions should be the same, or we can convert it to percentages if you like percentages better. What is the percentage here? It's mostly oxygen. What is the percentage here? 96.9%. What is it? We'll just calculate. 736.24 divided by 760 times 100. 96.9%. Both, right? I hope. And so this is the way. So if I did it here, if I do my I can do my calculation here. The moles of O2 is equal to the pressure of O2 times the volume of O2 divided by RT. Now you see the problem. You know, the problem is people get this mixed up all the time and use the wrong pressure and the wrong volumes all the time. You know, because I'll tell you, most students I know, they don't think of mixtures in terms of Daltons or Avogadros. They only think in terms of Daltons. But when we get to chapter 7, or 8, is it 7? Yeah, when we get to chapter 7, it's all in terms of Avogadros. All the mixtures we do are in terms of Avogadros. Okay. Because working with Daltons is too much hassle in chapter 7. Avogadros just makes your life easier. Avogadros makes your life easier because of things like this. Chapter 7 deals with a lot of chemical reactions. So if we take a look at a chemical reaction, you know, Avogadros is very nice to use in chemical reactions because if we have something like this, 2 hydrogen gases plus an oxygen gas yields 2 H2O liquids. Did I talk about this one already? Last time? Can I end with this? No? Okay, I didn't make it that far. This in terms of Avogadros is very nice. Because a mole ratio, 2-to-1 mole ratio, is the same thing as a volume ratio. And so rather than saying 2 moles to 1 mole, we could just say 2 liters, 1 liter, right? And so for every 2 liters of hydrogen, I need 1 liter of oxygen. Well, at what pressure? At constant pressure. And so they have to be the same. 2 liters at 1 atmosphere and 1 liter at 1 atmosphere. Gives me a mixture of 3 liters at 1 atmosphere. So I'm going to have 3 liters of gas here, and it's going to be at 1 atmosphere. Does that make sense? Okay, the other way of thinking about this is The mole fraction is the same as the pressure fraction and the volume fraction. And so the other way I could visualize this is if I took a 1 liter container and put 2 atmospheres of hydrogen and 1 atmosphere of oxygen, that would do the same thing, right? And so if I look at it in terms of this, if I pump in 2 atmospheres and 1 atmosphere, right, then I'm going to have a total of how many atmospheres? 3 atmospheres total. And what's the volume going to be? Let's say I have a 1 liter box. Yeah, it's going to be 1 liter of hydrogen, 1 liter of oxygen. 1 liter of hydrogen plus 1 liter of oxygen makes how many liters of mixture? 1 liter of mixture. And so you have to be able to flip very quickly back and forth, right? And you have to know what other people are talking about. Because, you know, once people start mixing these up, then forget it. Nothing's going to work. Right? And so we keep this separate. All right, now let's think in terms of Avogadros. 2 liters plus 1 liter is going to make how many liters? 2 plus 1 liter. They're going to react. So you have 3 liters of gas. It's going to react, and it's going to form how many liters? 2. It should form 2 liters, right? It would form 2 liters if it was H2O gas, right? But it's not H2O gas, it's H2O liquid. And since it's H2O liquid, it does not form 2 liters. It's much less than 2 liters, right? Much, much less. Let me give you an example. About how many liters is a mole of gas at 25 degrees C in 1 atmosphere? About. What's the molar volume of a gas at 25 degrees C in 1 atmosphere? 22.4? 22.4? No. 22.4, I'm glad you memorized that. But delete that from your memory because you'll probably use this more often. 24.45. 24.45. That's a much more useful number to remember to 4 sig figs. If you ever forget it, it's an easy calculation, right? V is equal to nRT over P. That's an easy calculation. And so we could do it this way. If I did it, okay, we're going to say about 25. And so if I took 50 liters of hydrogen and 25 liters of oxygen, then I'm going to form about 2 moles of water. 1 mole of water is 18 grams. 18 grams is 18 milliliters. And so this is going to form about 36 milliliters, or 0.036 liters, roughly, of H2O liquid. And so this is about 2 moles. 1 mole forms 2 moles of H2O liquid. 2 moles of H2O liquid is 36 grams. 36 grams is 0.036 liters, or 36 milliliters, right? And so we have to be careful because this only works for gases, the Avogadros. Solids and liquids are different. Okay, let's talk about the next topic here, which is kinetic molecular theory of gases. This is kind of divided into 2 parts. You know, all this, the ideal gas law, where did that come from? Ideal gas law. Did the ideal gas law come from theory? Was it derived from theory? No. The ideal gas law, people knew that before atoms, right? Because gases just behave this way. And so the ideal gas law is an example of what type of equation? Empirical equation. It's a law. Laws come from patterns, right? You saw the graph. Now we're going to talk about theory of gases, you know. And so a deeper look at why gases have, or what, you know, what is a theory again? Kind of yeah, explains things. It's a fundamental description of what's happening with a gas. And so this is kinetic molecular theory of gases here. And so let's look at some of the basic points. A gas is composed of a very large number of extremely small particles, you know, atoms, molecules. And these particles are in constant random straight line motion. So when we look at a gas, you know, we visualize particles like this, and they're moving until they hit something. And they're moving in straight lines until they hit something. Molecules of gas are separated by great distances. Yeah. A gas is mostly empty space. So the molecules themselves are extremely tiny. And so this is not very accurate drawing. The great distances, we're talking about atomic distances. So, you know, an atom's so small that the next atom might be way over here, which is huge in terms of atomic distances. But in terms of actual distances, it's not that huge. The gas, okay, the molecules are treated as so-called point masses. Are molecules point masses? That is, you know, when you look at a molecule, is it just a point, a tiny point in space? No, it isn't. Molecules have shapes to them. You've probably done VSEPR, right? Have you done VSEPR? Obviously. You must have done VSEPR. And so we know the molecules have shape, they have volume, and molecular volume. But this thing in the parentheses is a simplification. You know, what they do oftentimes is they simplify things so that math gets easier, whatever. And so rather than considering the shape of these, we just treat them as point masses. This simplification is pretty good because the molecules are so tiny. You know, that's what we call an ideal gas. As they have mass but no volume. And so we're assuming that the molecules themselves have zero volume. Is that accurate? No, it's not accurate. Molecules collide only fleetingly with one another and with the walls of their container. Most of the time, molecules are not colliding. So there are going to be collisions. Most of the time they're not colliding that's not so accurate because if you look at the frequency of the collisions, it's extremely high. These molecules are colliding huge number of times per second. There are assumed to be no forces between the molecules except very briefly during collisions. Okay, so what you're going to do is you're going to say that the molecules don't stick. They aren't sticky or they don't repel each other. You know. And so when they have collisions, they just bounce off each other. Like the difference would be, let's say if you threw a wet clay ball at the wall, it might stick to the wall, right? Whereas if you threw an elastic ball, you know, kind of rubber ball at the wall, it would bounce off. And so we call those collisions, you know, the ones that stick. What causes the clay to stick? Well, attractive forces. You know, the clay is attracted to whatever the wall is made out of there. We call those inelastic collisions, and the ones that bounce off are elastic collisions. We're saying that, you know, these don't get stuck to the wall or stick a little bit, and they don't get stuck to each other. They just bounce off. All right. So this is kinetic molecular theory of an ideal gas. There are two things that make a gas ideal or idealized gas. One is that they have zero volume. Two is that they have no attractions or repulsions. And so, kinetic molecular theory of an ideal gas. We can use it. You know, there's another way to get the ideal gas law or Boyle's law or Charles' law. We can get that from theory. You know, the kinetic molecular theory of gases. When we do that, we can get all the motion, and then we can derive these laws, you know, like Boyle's law. And so theory should be able to give a fundamental picture, you know. And so in this theory, we have, you know, collision frequency, speeds, molecules per volume, you know, and then these collisions, during collisions, there's momentum transfer, which is mass times speed, and we get pressure. And going through all this, we come up with Boyle's law. And so theory should be able to do this because it should give you a fundamental description of what's happening. And so originally Boyle's law was not derived from theory, right? Originally Boyle's law was derived from what? I'm sorry? Observations, right. Yeah, then an empirical, right. It was just derived from observations. Here you can see Boyle's law being derived from theory, you know, the physics of motion here. Are we going to do this? No. Are you going to be responsible for this? No. But it's interesting, you know, because it shows it being approached from both ways. The original way from observations and an alternate way from the theory. Okay, what are we going to be responsible for? Well, in this visual picture, if we have a gas at 25 degrees C, actually, I don't even want that gas. Let's get this. Okay, let's this is kinetic molecular theory now. Let's look at an example where we're going to have the oxygen and water vapor in a container. So we have H2O gas, and we have oxygen in here, in this mixture. We have O2 gas. And so, at 25 degrees C, these molecules are moving in straight lines and then colliding. This mixture is mostly empty space, right? If we were to treat this as ideal, what's the volume of a water molecule? Nothing. It's zero. Is that true? Well, the water is the blue, and so we'd have to say it's just a point with zero volume in there, so we'll shrink it down. Now, is that a reasonable assumption to assume that the volume is zero? Well, it's reasonable because the molecules are so tiny. Now, the volume is practically negligible, right? It's not really true because let's say I had a mole of water vapor. A mole of water vapor, if I were to liquefy that into a liquid, a mole of water would be how many milliliters? A mole of water is 18 grams. 18 grams is 18 milliliters. And so, you know, if there's a mole of water vapor in here, that mole of water vapor actually does have a volume, 18 milliliters. But hopefully the container is so huge that 18 milliliters is negligible compared to the overall volume of the container. Now, is the volume of the container always so huge? No. And so is that assumption always so good? No. The assumption goes bad at some point. You know? And the same thing with oxygen. Well, oxygen's very tiny too. And so as long as the container is big and we don't have that much oxygen in there and there's lots of empty space, then that assumption is pretty good. Because if we were to collect all the oxygen molecules and liquefy them, maybe it's not that big of a volume, right? It would occupy. But the volume is a little bit more because even a liquid, does a liquid have empty space inside here? Or is that just all condensed space? Is there any empty space between the molecules in a liquid? Yes, there is. There's empty space. When we're talking about the volume of the particle itself, there's no empty space because we're looking at one individual particle, not how the particles pack together. When particles pack together in a liquid or a solid, there's always gaps. And so if you look at let's say you look at a water molecule, we can't pack water molecules into a box without little gaps. It's like if you pack oranges inside a box, are there gaps between the oranges? Yeah, so if you pack oranges in a 1 cubic foot box, there's a lot of empty space in there. Right? We can do the gaps. Well, the same thing, but we'll talk more about that later. All right, what else do we want to know? Well, this gas is at 25 degrees C. And so the next thing we want to know is this. You know, there's motion here. Are all the molecules moving at the same speed? You know, the gaseous water is at 25, the gaseous oxygen is at 25. This is at 25 degrees C, this is at 25 degrees C. Are they moving at the same speed? Well, let's first look at the oxygens. So I'm going to separate out the oxygens. This is oxygen at 25 degrees C. Are all the oxygen molecules in this box moving at the exact same speed? Or are there some slow oxygens and some fast oxygens in between? It turns out at 25 degrees C, the temperature is equal to some stuff times the average kinetic energy. So I'll just say the temperature is proportional to the average kinetic energy. The average kinetic energy, it's an average because not all these molecules are moving at the same speed. You just have an average. And it turns out that some of the molecules are moving slow, some are moving fast. We just look at the average. And so not all the oxygens are exactly the same. In fact, if we look at the population versus the speed, we see a distribution that looks like this. This looks very similar to the kinetic energy distribution I showed earlier. But this is what we call the speed distribution. Shape is exactly the same. It looks like a thermal population distribution, right? Where there's a little high energy tail here. And so some of these molecules are moving quite fast, very fast. In fact, what is this gas here? I don't say, but you know, 4,000 meters per second. 4,000 meters per second. 4,000 meters. About 3. That's moving fast, 4,000 meters in a second. And some of them are moving a lot slower, you know, down here. But we have an average speed, which is given by this. Average speed. You would think the average speed would give you the average kinetic energy, but it doesn't. The average kinetic energy, you know, the average energy of this is not based on the average speed. You know what it's based on? kinetic molecular theory, the average kinetic energy, E bar K, is equal to 1/2 times the mass of the molecule times the velocity. But it's not the average velocity, it's what we call the RMS velocity. And it's going to be squared. U RMS is equal to the root mean square speed. Root mean square speed. So you take the average mean, square root, something like that. You don't have to worry about that too much. Except that the RMS is what we're going to be most interested in, is because that's going to give us the average kinetic energy. And so the RMS speed, how would you think about this? One way of thinking about the RMS speed is the effective speed. The effective speed is this. If you could, rather than having slow ones and fast ones, if you give all the molecules the same speed in the mixture and have it at 25 degrees C, what would that speed be? That speed would be the RMS speed. That would be the effective speed of this collection of gas particles or molecules. That's one way of thinking about this. So what are we going to do? Well, we are not going to calculate the distribution, although it's not so difficult, this math. But we're going to do some calculations for things that we're going to be interested in. There are lots of calculations in kinetic molecular theory, but we're going to focus on a couple of them and then try to visualize this mixture or gases. And so, the H2O gas is at 25 degrees C, and the oxygen gas is at 25 degrees C. So both of these gases are 25 degrees C. And so, since both of these gases are 25 degrees C, it means that they both have the same, what? You know what they both have the same of? Equation 621 or box 622. What's equation 621 showing? 621 showing that the average kinetic energy is equal to, this is for an ideal gas, is equal to 3/2 RT over Na, where R is the gas constant and Na is, no, Avogadro's number. R over Na is a big constant in physics called the Boltzmann constant. And it's usually given the symbol K. We don't have to introduce the Boltzmann constant here, so we're just going to call it R over Na. And so in terms of the Boltzmann constant, E bar K is equal to 3/2 kT. So 3/2 kT, where K is R over Na. And so this 3/2 K is just a constant. And so E bar K is just equal to the, or proportional to the temperature. And so what this means is that the average kinetic energy of water is equal to the average kinetic energy of oxygen. Why? Because they both are at the same speed. They're both at the same temperature. So let's go ahead and calculate the average kinetic energy for these. There are two ways we could do this. We could use this equation, but there's one more equation we can get that you should know. And so what is that one more equation? The one more equation is URMS. We aren't going to figure out the whole distribution of speeds, but we want to know how we can determine URMS. And so that's going to be equation 620. Let me find that. Here we go. Equation 620. So URMS is equal to, well, I better write this, where K is equal to R over NA. URMS is equal to the square root of 3RT over M, where M is the molar mass. So we have a couple of options. If I want to figure out what is the kinetic energy, the average kinetic energy, I can calculate it using this equation here. Just plug in R over NA. This would be the thermodynamic R, the kilojoules one. And so R would be 8.3145 joules per mole Kelvin. And then we'd have to know the physics definition of a joule. You know the physics definition of a joule? This is where 1 joule is equal to a kilogram meter squared per second squared. You heard that? And then we can plug that in here, over here, because R would just equal 8.3145 kilograms meter squared per second squared. Or actually, we don't. Do we have to change that? No, we don't have to change that. We don't have to change that because if you look at the units would be in joules per mole Kelvin. Well, joules per mole Kelvin, if we plug that in here, we get 3/2 R over NA times T. R has the units of joules per mole Kelvin. Has the units of joules per mole Kelvin. Avogadro's number has the units of Avogadro's number, NA, has the units of, I skipped this entirely in chapter 3 because I thought Avogadro is so simple. But what are the units on Avogadro? 6.02 times 10 to the 23rd per. 6.02 times 10 to the 23rd. 6.022 times 10 to the 23rd per mole. And so Avogadro's number has the units of moles to the -1. T has the units of Kelvin. So moles cancel, Kelvin cancels, and we're left with joules. So maybe we could have derived this equation just using dimensional analysis. Well, anyway, we plug in 298 Kelvin. Actually, can somebody do this? plug in 3 halves R, 8.3145, Na, 6.022 times 10 to the 23rd, T, 298 Kelvin. Units cancel, leaving us with joules. What's the average kinetic energy? .17 times 10 to the negative 21 joules. 10 to the negative 21 joules, is that much energy? If you need to heat 1 gram of coffee by 1 degree C, you would need 4.18 joules. It's 1 gram of coffee, 4.18 joules. If you need to heat up, let's say 250 milliliters of coffee, which we'll call about 250 grams, you'd need 250 times about 5, which would be about 1,200, about 1,200, 1,300 joules to heat up a cup of coffee by 1 degree C. Is that much energy? There's got to be a mistake, right? Is there a mistake, you think, or does that sound right? It's not much energy, is that? 10 to the minus 21 joules. If somebody were to give you 10 to the minus 21 grams of, actually, could you have 10 to, is it possible to have 10 to the minus 21 grams of gold? Is that possible? 10 to the minus 21 grams. Ten to the minus 21 grams of gold. Well, how much does gold weigh? We'll just say about 200 U. This is just scale. If a gold atom weighs about 200 U, how many grams is that? Well, we know that 1 gram is 6.022 times 10 to the 23rd U. And so 200 over 6 would be what, roughly? 3? Let's say roughly 3. 3 times 24 would be 330 times 10 to the